Vitamin D is not a vitamin, it's a hormone. It is not necessary to prevent. Good morning, friends. In this video, you will learn why vitamin D is not really a vitamin at all, not even for people of European descent. But before we talk about that, please subscribe to the channel if you're not already, like the video, and comment on the video to help the channel's growth. Now let's get started. First of all, what we learned so far is that vitamin D was originally termed a vitamin, like other vitamins, because it was thought that in its absence, human beings necessarily developed a certain disease pathology. In the case of vitamin D, that is rickets, a softening of the bones, a problem in maintaining bone mineral density. However, we quickly learned that this was not the case in all people. For example, people of African descent seemed particularly resistant to the effects of low levels of vitamin D on their bone mineral density. And that's also true for other ethnic groups. So it seemed to be the case that vitamin D was only a vitamin for people of European descent. But is this true? It isn't. In this video, we will survey the biological processes by which vitamin D affects calcium homeostasis, briefly, in order for me to show you that the vitamin D system is built beautifully in the human body, with multiple points of negative feedback loops and ability to gain slack, such that low vitamin D levels are not as instrumental in the development of rickets alone as we think. And once you learn to envision the vitamin D system in calcium homeostasis, you will realize that vitamin D is not really a vitamin at all. It's a hormone that modulates about 3% of the genes in our genome. And you'll also learn why certain kinds of genetic variation could potentially provide even more slack and make it even more difficult for people to develop rickets singly from the absence of vitamin D. Let's get started. First of all, vitamin D is a master regulator of calcium homeostasis, but it modulates calcium homeostasis through metabolites whose expression is differentially regulated by our lifestyles and our genetics. Moreover, the vitamin D system has slack within it, such that it modulates itself in hypovitaminosis and in hypervitaminosis D. In this video, we're going to review three major pathways by which vitamin D modulates calcium homeostasis, beginning with its effect on calcium absorption in the intestines. You see, vitamin D's so-called active metabolite, that is the metabolite with the greatest potency at the vitamin D receptor, 1,2,5-OH2D. That metabolite, which I formerly called the kidney metabolite, by the way, to get into a little bit more detail, that metabolite is also synthesized in other parts of the body, but mainly in the kidney. That metabolite governs intestinal absorption of calcium, and it also modulates phosphate metabolism. This active metabolite, which we'll continue calling the kidney metabolite of vitamin D, does so through its genomic action on the vitamin D receptor located in the intestines. The vitamin D receptor in turn modulates certain proteins like TRPV6 and CABP, in turn causing increased intestinal absorption of calcium. But even here, vitamin D's modulation of these two genes is not necessary for calcium absorption. Rodent models in which rodents are KO, meaning they have knockouts of these two genes, those rodents still are able to absorb calcium perfectly fine and have good calcium status as long as they're not fed a calcium deficient diet. Before we move on, I'd also like to mention that this same kidney metabolite also regulates renal, that means kidney, reabsorption of calcium through other genes like TRPV5, NPT2C, as well as clotho. But we won't get too much into that here. Moving on, vitamin D also regulates growth pathways. It regulates the IGF-1 effects on bone, and it regulates the GH effects in bone. In particular, in some contexts, when rodents are vitamin D deficient, IGF-1 and GH have lesser effects on bone mineral density. Here, vitamin D seems to be more important to IGF-1's effects than it is to GH's effects. For example, it modulates 3 of the 6 IGF-1 binding proteins, specifically 1, 3, and 5, some of the most important IGF-1 binding proteins. Vitamin D also modulates the Wnt pathway, which is a major growth pathway, and how it has some of its effects on hair, which we'll get to in a future video. But the most powerful mechanism by which vitamin D modulates bone mineral density is actually by its regulation of another hormone called parathyroid hormone, PTH. You see, when vitamin D levels are low, parathyroid hormone rises. But the same also happens when calcium levels are low. And also the reverse happens. When vitamin D levels are sufficient, parathyroid hormone reduces. But also when calcium levels are sufficient, parathyroid hormone reduces. Which one is the most important? We'll see soon. When parathyroid hormone rises, osteopontin rises too, the siblings protein rises as well, pyrophosphate rises as well, and due to these causes, as well as low phosphate and calcium levels, in the end, bone mineral density worsens and osteomalacia or eventually rickets develops. Studies in Europeans show that Europeans that are deficient in vitamin D have much higher PTH levels. Europeans that are insufficient in vitamin D also have higher PTH levels, and Europeans that are sufficient in vitamin D have normalized PTH levels. And it's been discovered that to normalize PTH levels, something around the blood level of 20 nanograms per deciliter would be required. But it's been found that in Europeans, bone mineral density is sometimes not optimized until they reach blood levels of 30 nanograms per deciliter. Before we leave this subject, I'd like to point out that vitamin D is not required to lower parathyroid hormone in the presence of sufficient calcium in the diet. What does that mean? Calcium is a safeguard against vitamin D's effects on parathyroid hormone. And if you're eating enough calcium, you don't really have to worry about vitamin D's effects on parathyroid hormone. Next, let's talk about genetics. How could someone's genetics, there are many ways. There are dozens and dozens of SNPs that affect vitamin D status. But let's look at a simple model. How could someone's genetics affect the activity of their vitamin D, such that somebody could have lower levels of vitamin D, but have an equal sort of signaling effect from the vitamin D as someone with higher levels? Well, for example, remember we talked about this the active metabolite, the kidney metabolite, right? The kidney metabolite is synthesized by an enzyme called 1-alpha hydroxylase. If somebody has more expression of 1-alpha hydroxylase, they would have a larger proportion of the very active potent vitamin D in their blood as compared to the less potent versions of vitamin D, compared to somebody else. On the other hand, this same very important metabolite is degraded by 24-hydroxylase. And a reduction of the availability of 24-hydroxylase would mean that you would have more of that potent metabolite available. So polymorphisms in the genes that encode these two enzymes could easily make somebody, like somebody with African descent or somebody with Indian descent, able to survive with lower vitamin D levels while still getting very powerful vitamin D signaling. And that's aside from the fact that, as we just learned, calcium is independently a safeguard against all of these issues. Let's talk about slack next. First, what is slack? Well, slack is, if you build a system, you have sometimes input variables and an output variable, which is your desired variable. If you build the system to be robust, such that it can yield you the desired output variable given changing input variables, we call that a system that has slack. I came across this term in operations research. I don't really know if it's used elsewhere, but I'm just gonna introduce the term here for the vitamin D system. What does that mean? The vitamin D system takes care of itself. Let's begin with the fact that the active metabolite isn't really the only active metabolite, as you guys know. This kidney metabolite is degraded, remember, by 24-hydroxylase into 2,4,2,5-OH2D. But that metabolite is also active. That metabolite actually improves bone mineral density through its regulation of a gene. Next, our first negative feedback loop, beginning with parathyroid hormone. Remember, when parathyroid hormone rises when you have low vitamin D levels. Parathyroid hormone rises, right? And then causes us some problems. But as it rises, it actually modulates, remember that enzyme that creates the potent kidney metabolite, that 1-alpha hydroxylase? Its expression is elevated by parathyroid hormone. So when you have low vitamin D levels, your body within a person, irrespective of your genetics, your body increases the expression or the proportion of the active potent metabolite that really you desire there. So if your body senses low vitamin D levels, it increases the portion of those levels that is going to be active. And this is done through the parathyroid hormone negative feedback loop. Let's review what we just said to be clear we understand what's happening. A negative feedback loop is when in a system you have one variable that, for example, say increases a second variable, but then this variable as a consequence decreases the first variable. So basically it's feedback that limits the activity of a system built in within it. We have that in the vitamin D system. As we just discussed, the vitamin D system has a negative feedback loop to protect us from vitamin D deficiency. When vitamin D levels go down, or when calcium consumption also goes down, parathyroid hormone rises, and then parathyroid hormone affects the genetic expression of the enzyme that produces the most active vitamin D metabolite, therefore increasing the portion of vitamin D that is really active in our body. The reverse also happens. There's another negative feedback loop that protects us from excess vitamin D levels. In particular, when vitamin D is very high, something called fibroblast growth factor 23, which is a growth factor. By the way, there are some very interesting fibroblast growth factors. We should eventually do a series on them. But fibroblast growth factor 23 has sort of opposing effects to PTH, parathyroid hormone. So what's this second negative feedback loop? Well, when vitamin D levels are high, but also when phosphate from the diet is high, fibroblast growth factor goes up. It exerts an opposing effect as parathyroid hormone. It, in turn, reduces the enzyme's activity that synthesizes the active vitamin D metabolite, such that now a smaller portion of your vitamin D is really potently active, but it also increases the activity of the degradation enzyme that degrades that active metabolite. So through two genetic mechanisms, it reduces the potency of the vitamin D levels you have within you when you have too much vitamin D levels. But notice, both of these negative feedback loops are also modulated by dietary calcium and dietary phosphate. So there are two lessons here. The first is that vitamin D controls itself. When you have too much vitamin D, you reduce the amount of the active metabolite in the proportion of the total vitamin D levels. When you have too little vitamin D, you have more of that potent metabolite. So the system takes care of itself. But the second lesson, very important as well, is that vitamin D isn't required for any of this. Calcium deficiency in your diet will also raise parathyroid hormone and do the same thing, and phosphate excess in your diet will also do the same thing as having too much vitamin D. Next, vitamin D is not even sufficient to inhibit rickets by itself. It's been shown, for example, in a recent Cochrane review, a meta-analysis. Cochrane reviews are excellent meta-analysis. I highly recommend them. A recent Cochrane review found that vitamin D supplementation in older people was not sufficient to lower fracture risk by itself, but it was when combined with supplemental calcium. Also, it's been shown that vitamin D supplementation can't inhibit rickets by itself at dietary calcium levels less than 300 milligrams. So vitamin D isn't sufficient by itself to prevent the disease state that it was defined as a vitamin because it prevents. But is it necessary? Is vitamin D even necessary to prevent rickets? It isn't. In vivo studies show that in the absence of vitamin D, you can have completely normal, healthy bone mineralization. As we already discussed, parathyroid hormone can take over the activity of the vitamin D receptor in its absence, in the absence of vitamin D signaling. Rodent studies show that rodents completely missing the vitamin D receptor, given a diet high in calcium, phosphate, and lactose, because by the way, lactose improves calcium digestion. We're going to talk, I might do a series on milk and lactose in the future. But anyway, given this diet with high calcium, high phosphate, and lactose, rodents missing the vitamin D receptor develop completely normal, healthy bone structures. This also happens in rodents that are completely missing the enzyme that synthesizes the active metabolite of vitamin D. So these rodents don't have 1,2,5-OH2D. They don't have the most active metabolite at all throughout their lives and still develop normal bone density only with a diet sufficient in calcium, phosphate, and lactose. So vitamin D is neither sufficient by itself to prevent rickets, and it's not necessary to prevent rickets. It's not necessary in Europeans either. Let's review what we learned here. First of all, vitamin D regulates itself. It exists in a beautifully designed vitamin D system with negative feedback loops and slack built within it. This is important to understand because in future videos we will review dose responses in humans to vitamin D supplementation. You will see that higher and higher levels of vitamin D supplementation don't seem to be more and more effective. They have diminishing returns. A lot of these diminishing returns and also studies that show the inefficacy of supplementing vitamin D may be due to these exact issues of the vitamin D system that we discussed in this video, which by the way I don't think anyone has ever discussed before on video. So officially you know more about vitamin D than anyone you know probably. And second, what we learned is that vitamin D is not a vitamin, it's a hormone. It is not necessary to prevent rickets. All that's necessary is sufficient calcium and phosphate absorbed in the diet, and that can be done even in humans probably with just lactose. Anyway friends, I hope you found this interesting. The last video was not as fun, but hopefully this one surprised you more. I look forward to seeing you again this afternoon.